Good morning. Welcome to Krishna's classroom. We continue with our exploration of the absolutely continuous functions and how they are related to functions of bounded variation. Now we have seen that functions of bounded variation can be written as on a compact interval, can be written as the difference of two increasing functions, and therefore the derivative exists almost every. So this is one outcome of that. Now it was found that probably that bounded variation, the demand that the function should be of bounded variation imposes some restrictions on the rapid oscillations of the function, so that the differentiability is not very badly affected, or the non-differentiability is confined to a set of measure 0. However, when it comes to the next level, namely whether the fundamental theorem of calculus is valid for such functions, then there is difficulty. Now recall that and it is in this context that we introduced another concept, namely absolute continuity on the compact. How far this helps us? This is a question that we want to ask. And we would like to also explore, while absolute continuity deals with the behavior of the function on too small a set, not too big a variation that you would have. This is roughly the content of the absolute continuous functions. Okay, that is true all over the space. Now, so the question is, if you have examined the definition of absolute continuity, you see that this is what said. It is slightly more stronger condition than mere continuity. It says on any set of small measures, the variation of the function is also small. A crude way to put it. But such a restriction we have not put on functions of bounded variation. It merely talks about avoids wild variation or wild oscillation of functions. Okay, that's about that. Now, let us, in this context, the function that we have already looked at is the Cantor-Lebesgue. So, recall that we have shown that the Cantor-Lebesgue function phi on the interval 0, 1 is an increasing function is a continuous increasing function which is also continuous which is a continuous increasing function. Therefore, it is a function of variation denoted by it's a function of boundary variation. And we proved that this fails to be absolutely continuous on the interval 0, 1 and designated by AC 0, 1. Therefore, it follows that f is a function of bounded variation on the interval AB does not imply it is a function of it's an absolutely continuous. Now, in this context, we also proved that we have seen that all Lipschitz functions are absolutely continuous yes. However, there exists absolutely continuous. Which are not elections. Then let us denote this by Lipschitz on the interval, that is on the compact unit. Contained, is properly contained, absolutely continuous. This we have already. Now this is a outcome of our earlier analysis. Now what we are exploring in this talk is the relation between absolutely continuous functions and functions of bounded variation. Already we have seen that there exists bounded functions of bounded variation on interval AB which are not absolute continuous. So as far as the existence of the derivative almost everywhere goes, you see, it's fine to see that the functions of bounded variation are good enough. But then, if we were to go further and ask whether the fundamental theorem of calculus is valid, then of course it appears we need some further restrictions on this. For example, the very function that we have discussed just now, which is the Cantor-Lebesgue function, does not satisfy the fundamental theorem of calculus. That is integral over 0 to 1. Phi is equal to 0 because you see that the function is almost everywhere a constant, and its growth is confined only to the Cantor set. And you see that then this integral becomes 0. And this of course is less than because phi 1 is so this is not, I mean, you don't get equality there from this function. Therefore, it also shows that when it comes to seeking the conditions on functions which are amenable to the fundamental theorem of calculus, you have to really put further restrictions on the functions of bounded variation. Okay, so this shows remark. This shows that for the Cantor-Lebesgue function, The fundamental theorem of calculus does not hold. So that shows that with just mere existence of the derivative almost everywhere is not going to assure us that the fundamental theorem of calculus would be valid for that function. Okay, so that's a very fascinating example. Therefore, some further restriction had been brought on the functions of bounded variation. I mean, we have not proved the relevant data. In the next theorem, we are going to prove that. But before that, to see that we want to show that absolute continuity on compact intervals assure that such functions are functions of bounded variation. Okay, and that also helps us to show that prove the following, that it can be split into two functions of bounded variation which are increasing on the interval AB, and therefore it is differentiable, or the derivative exists almost everywhere. Sorry, this is phi derivative I am talking. Phi derivative, sorry, not phi. Okay, right. Sorry, I made a mistake. Please note that I have corrected. Okay, right. Therefore, now you see that the question is, and what have we done? We have imposed conditions on the function that on sets of small measure, the function, the variation, the total variation of the function is also of small. This is what we have assumed. It's a further restriction, and therefore later we shall see that this indeed works. And the first step is now this: is a function of which is absolutely continuous on a compact interval AB a function of bounded variation? So the question that we ask is this: continuous on a compact interval AB a function of bounded variation. If So you have several advantages because functions of bounded variation can be expressed as the difference of two increasing functions. And what more is that you see that both these component functions which are increasing are almost everywhere differentiable. So we are assured that the derivative exists almost everywhere for such functions. And then of course you can ask whether the breakup that you have obtained are also functions which are not only functions of increasing functions, but they are also of absolutely continuous function. We have seen that mere condition that a function is increasing on the compact interval does not assure you that it is a function of bounded, a function which is absolutely continuous. In the case of the Cantor-Lebesgue function. Okay, so we have the following theorem. So this is the theorem that we are going to prove. Let the function f be absolutely continuous will be on the compact interval. Then f is the difference of increasing absolutely continuous functions. Absolutely continuous functions further f is a function of bounded variation. That means belongs to AB. This is the statement of the chair. Now let us try to prove this here. Obviously, we find a way out because we have some nice results on the functions of bounded variation. Therefore, the first job is to ask whether an absolutely continuous function is a function of bounded. Proof. Step 1. F implies F belongs to bounded variation, is a function of bounded variation on the interval. That's the first one. This is what we do. Of course, what is the advantage? The advantage is that we can apply results that are already available on functions of bounded variation and break it up as the difference of two increasing functions on the interval. Okay. What is the consequence? The consequence is that we can use an earlier result. It says that these two portions, that is, if we write F as difference of G and H, where both G and H are increasing functions, then you know that G is differentiable almost everywhere, H is differentiable almost everywhere. Therefore, G minus H is differentiable almost everywhere. That is, F is differentiable almost everywhere. So the derivative exists almost everywhere. Okay. And then, of course, that's an outcome of this exploration. And what more? So you can ask the next question. The breakup that you have obtained could also have the possibility that they are also absolutely continuous functions. Or can you have this breakup that you have devised as functions of bounded, not only bounded variation, not only increasing, but are they absolutely continuous? Because we know from the Cantor Lebesgue function that mere increasing does not imply that the function is an absolutely continuous function. Okay. So that's the step 1. And step 2 is simple. Then where G and H are increasing, AB, and hence of bounded variation on AB further are differentiable almost everywhere, and hence f derivative almost everywhere. That is a step. I mean, this is just merely two steps using a previous theorem. And step theory 3 will be the way in which we define G and H. Okay. The breakup is that both G and H are absolute. Or in other words, we can split up f as the difference of two increasing functions which are absolutely continuous on the interval. So that completes, that's the stages of the. So let us now start with the step 1. Then f belongs to okay. So what we do? How do we proceed? Make use of absolute continuity. You conclude that it is a function of all. It's not difficult at all. Just use our definitions of the property of absolute. Now, f absolutely was implies for the choice of epsilon equal to 1, there exists positive and in the definition of absolute. You have a disjoint partition, say, whose into partition, you have a disjoint set of intervals whose total length is less than delta. Then the values of f summed up on these intervals would be, or the variation of this f worked out on this interval is going to be less than epsilon. So let P be a partition of AB into n closed intervals one to n, each of length less than n. Now this is possible because you are working on a closed bounded interval. Then what can you say about the total variation f on the interval ck dk is less than or equal. Okay, so that actually tells about we are using the condition of absolute continuity, and this is your epsilon, and the length of this interval is dk minus ck is less than delta. Therefore, the function, the total variation of the function on this interval is going to be less than or equal. So that's the crucial result. This is also the point. That implies, let us work out the total variation by the additivity of total variation the function f a x we have k, and each one is less than 1, therefore this is less than or equal. That implies f is of bounded variation on the interval. So absolute continuity implies that the function is of bounded. So now we are in a position to go to the step 2. In step 2, we use the following. Since maybe f can be written as the difference of two increasing functions, or to have fx equal to minus that's the breakup that you have. And you see that you have seen this, that this is what we have proved in the previous result, that this is an increasing function, this is an increasing. Say so now what we have a breakup, therefore you see now G and H so this is your G, this is your G, this is your increasing functions, and hence all the equation. Therefore they are G derivative, H derivative exists almost everywhere. That is f derivative exists almost everywhere on so we have used that to prove this, to conclude this. Now what next? The next step is to show that both these components G and H are absolutely. Step 3. Now we shall prove that. Okay. Claim total variation function is absolutely fixed. Therefore, if that is so, then of course f is assumed to be absolutely continuous. Therefore, this is also absolute. So we would have got g also absolutely continuous. Okay. So let us work on this. Let once again listen. Now choose delta positive axis corresponding to epsilon by 2. Continue. Let be a disjoint collection of intervals you have used n for which let pk partition of the interval ckd, specific interval ckd, some partition for one by the choice of delta And in the context of absolute continuity of f on AB, we have the total variation that is just merely writing down the condition for absolute continuity. Now take supremum over pk varying over all partitions of ck. Then what we get is the following, that is sigma k equal to 1, sorry, total variation of f on the interval ck is less than or equal to epsilon by 2, which is less than epsilon. Now we make the following observation, that what exactly is this TVFCKD? Now for this is equal to the total variation of f CK. Delta. we have we have we have this is less than this. What have we shown? We've shown that is an absolutely continuous function on AB. This is what we wanted to. That is in our notation. H is absolutely continuous. Therefore, F plus H is also absolutely. Now, AB. Therefore, it implies F plus H. That is thus the components to which we have split F into are functions of which are again absolutely continuous on the interval. So that completes the proof. I've already talked about the example. Therefore, we have is strictly contained in now that is our conclusion. It's not they are equal because you already pointed out that. So hence we have eventually Lipschitz conditions on the interval AB, Lipschitz functions on the interval AB are all absolutely continuous on the interval AB, and there again this is not equal to, and here again you have this is not equal to, not equal to functions of bounded variation, but it's a part of it. So that completes this talk, and I'm likely to take a break at this stage for about 10-15 days. I will be away in Bangalore. And after that, we will continue exploration. Thank you very much.